Unit 1 Chemistry, Chapter 8, looking at carbon lattices and nanomaterials. So in the previous chapter we looked at molecules, okay, which is things like carbon dioxide, where you've got a distinct number of atoms bonded together. You can also, however, get lattices, like our ionic or metallic lattices, but with covalent bonding in them. There's two different types we can get. We can get network lattice, okay, where each carbon is covalently bonded to 4 others, and it just keeps on going like that. That would be a diamond. Or we can get a layer lattice, where each one is bonded to only 3 others, and we actually have one delocalized electron from each carbon. And this makes one layer of lattice, which is then attracted to the next one by dispersion forces. This would be a layer lattice and graphite that you've got in your pencils in that. Both of them are pure carbon, okay? But the structure is very different, which means that the properties are very different, yeah? And the value we place on them, therefore, of course, is very different. Don't try and ask someone to marry you with a ring that's got graphite in the stone, because you're not going to get as good a response. Yeah. So, in the network lattice, we've got a regular tetrahedron throughout the lattice, no weak links, nothing charged, only covalent bonds. This makes diamond one of the hardest substances in existence. Graphite is hard in one direction but soft in the other. So we've got those layers, and in each layer you've got carbon bonded to 3 others. And we've also got a delocalized electron. That delocalized electron means that within a layer we can conduct electricity, just like in a metallic lattice. But between one layer and the other, because it's non-polar, we've only got intermolecular forces and we've got dispersion forces, so the layers can slide off. So when you're writing with a pencil, you're actually sliding off one layer after another of your covalent layer lattice. So when we compare them to the molecules, they've got higher melting and boiling points, and they tend to go straight from a solid to a gas if they're high temperature. So we don't have a liquid state. We get them to a really ridiculously high temperature, we break all the covalent bonds at the same time. If they're layer lattices, they can conduct electricity. Okay, network lattices never can. And they are much less reactive than the small molecules. Now, sometimes these lattices can be used to make nanomaterials. So if we take one layer of graphite, that's called graphene. We can roll that up to make a carbon nanotube. We could also take one of these, where each carbon is bonded to 3 others, and turn it into a ball structure, and we call that a fullerene. Okay? Or we can get the layer lattice, the network lattice, and make little tiny crystals, but they're still lattice structure. We call that nanodiamonds. Okay? Fullerenes or buckyballs, hollow tubes or hollow circles within them, they're really unreactive. So in theory, we could use them as a drug delivery system. So hack your drug within them, send them into the cells so they only attach to the cancerous ones. It would mean that you wouldn't get anywhere near the tissue damage that you get from something like radiotherapy.